So, in the previous example, what have we done is that we consider some random choice, x. We choose x at random, and that gives us some object. And this object, we consider its size, then we consider the expectation of that. And we compute that expectation and then show that there exists some choice of x which give us this set which is as large as its expectation. So which is a typical, typical technique that we will use. So we consider expectation of something, and then we compute it using some property of this, and then we conclude that there must be some random choice which does as good as the expectation. So that's a typical technique. So let's make this a bit more rigorous and then see some examples on how we can actually use the expectation to show various problems. So let's give some name on this object that we defined before, which is determined by some random choice. We say a function x defined on a probability space is called a random variable. The range of this could be anything, but many cases range of this random variable is usually real number. But not always, not necessarily always. So this itself is a random variable. We make some random choice x. We choose x at random, and then depending on that, we get a set. And this set is a random variable, but also size of this is also random variable, which has a real number value, real value. And then here what we did is that we consider the expectation of this random variable, and then we show that there exists a choice which does as good as the expectation. And we define the expectation of x. Let's say this is a discrete probability space, because that's the, we only will deal with the discrete space. Not only, but essentially we will mainly deal with the discrete probability space. Then this is, definition of the expectation, where the E runs over all elements of the discrete probability space. And one of the observation, one of the property that we know is that when x1 and x2 and xn are all random variable, so xi random variable which taking the real value, then this x is also a random variable. And moreover, we have this formula which is called linearity of expectation. So this will allow us to compute the random variable, expectation of a given random variable in a more easy way. And also what we know is that if this is given, if this expectation is C, then there always exists a choice which we make in a random way, such that this random variable is at least as large as C, and also there exists a choice with this being at most C. Let's consider some example on how we can use this. Let's not give the name, give the number. So max cut problem. So let's first consider this problem. When we have a graph given, G with m edges, what is the maximum number of edges in a bipartite graph G? So if G itself is bipartite, of course we can have a maximum number m, same as the number of edges in G. But if it's not bipartite, then how well can we do? Or in other words, what is the maximum number of edges in the induced bipartite graph? We take B1, B2, a partition. So we take a partition of the all vertex set, and we consider the edges between, and we delete the edges inside. And we consider this only the number which is crossing between. Then what's the maximum over all partitions? So that's why it's called the max cut problem. We want to cut it into two so that the edges between is maximized. And in undergraduate graph theory, we learned the theorem, this following theorem, but I don't remember whether it was proven in probabilistic way. So let G be a graph with m edges. Then G contains a bipartite subgraph with m over 2 edges, at least m over 2 edges. So this can be proven either using probabilistic method, or we can also consider the max cut. And then, so max cut is the partition which maximizes the crossing edges. And then you can argue from the property of this to actually show this statement. But let's use the probabilistic way to actually prove this. We read a partition. We choose a partition at random. Partition of the vertex set obtained in the following way. So for each V, which is the vertex in G, we add V to A or B independently at random, and of course uniformly at random, meaning that the V is added to A or B with probability half, and that's independent. So for several different vertices, they belong to the which set is independent event. And let X be the number of crossing edges. So edges of the edges between A and B. So call XY crossing if exactly one of them is in A and the other one is in B. Then this X is actually summation of indicator random variable, where XE is 1 or 0. If E is crossing, it is 1. Otherwise, it is 0. So we say on a random variable is indicator random variable if this is always taking value 0 or 1. And the event where it is 1 is some event. And this is the indicator random variable of this event. That's how we call it. So this XE is the indicator random variable for the event where XY, which is E, being crossing. So that's the event that this becomes crossing. And then for that event, this becomes 1. And for the rest of them, it becomes 0. So it's indicating whether this event has happened or not. Then, what's the expectation of this indicator random variable? For indicator random variable, the expectation is easier to compute. So let's say the event itself is A, then you have the value of 1 or 0, and then one happens with probability, certain probability, and the other happens with the rest of the probability. Let's write it is 1 minus probability of A. Then this is same as probability of A, so it's easier to compute. This is half. The probability that this belongs to A, this belongs to B, or this belongs to B and this belongs to A is happening with probability 1/4. You add, then probability that E becomes, the specific HE becomes crossing is half. By the linearity of expectation, here, the linearity of expectation, it doesn't matter whether each summand of these random variables are independent or not. This is always true. And that's M over 2. Then, by the above property, there is always a choice which does as good as the expectation. So, there exists a partition AB of G with at least M over 2 crossing edges. So that shows exactly what we want. And how sharp is this theorem? If we consider a complete graph, then, no matter how you partition it into 2, the best way you can do is n over 2, n over 2. Let's say n is even. Then you can show that this n over 2 cannot be improved to any positive number epsilon. It cannot be improved to 1 plus epsilon times n over 2. So in that sense, 1 over 2 is best possible constant. But if you actually compute this in a more further, if you consider this complete graph and then you compute it in a more exact manner, the number of edges is n choose 2. And then we are assuming n is even. The number of edges between them is n squared over 4. And this n squared over 4 is actually m over 2 plus negative 1 plus square root of 8m minus plus 1 over 8. So this is m over 2 plus some sublinear term, some term which is real of m to the 1 over 2. So even if we cannot really improve this constant, one might ask that can we actually do better than this m over 2 with certain number. And that's actually a theorem by Edwards. Says that G has M edges. Then there exists A union B such that the number of edges in this bipartite graph is at least m over 2 plus negative 1 plus square root of 8m plus 1 over 8. So we will discuss about this in the next time. But here you see some typical technique. So we want to show that something exists. And something exists which, satisfies certain condition. So this quantitative condition can be encoded into this random variable. So this random variable measures some number, and then we want to show that there is a choice which makes this x as large as m over 2. Then how do we do it is we want to consider its expectation and then show that it's at least m over 2. For that, we decompose this into indicator random variable whose expectation is easier to compute. And by using the linearity of expectation, we compute the expectation and then conclude that there exists a choice which makes this random variable x bigger than or equal to this expectation. So that's a typical technique. So next time we will briefly discuss about this theorem, and then we will consider other examples of the problems that we will use the linearity of expectation to solve the problems.